Did you see the teaser trailer for the new Joker movie?
Joker movie?
Yeah, it's a DC movie that's just on the Joker itself. I don't even think Batman's mentioned in the whole trailer.
No, I'm not kidding.
It's really creepy. They're trying to keep it dark, like Dark Knight type stuff.
And who is the Joker?
Joaquin Phoenix, I think is his name.
Yeah.
It looked really good in the trailer. He seemed to do a good job. He did the laugh pretty well, so it's important. Is there a set date for when they're painting the lab?
They're here today, and they said, "Oh no, we'll come back next week to fix the wall, the hole in the wall." I hope next week by Gregorian calendar. Strange. Yeah. So.
It's interesting. They're just gonna paint everything except for that spot, and then come back to fix that wall and paint it over.
No, because then it might look uneven. No, if you don't paint the whole thing in one go. I hope we don't have to assemble the desks. But yeah, that's not too bad compared to what we did.
Yeah, I was telling my girlfriend about it. It was like, it seemed like everything fit together in some way, but we couldn't take it apart in a simple way, so we had to force it until one little part broke, and then we could take it apart from there. But each piece.
She's not an engineer, I guess.
No.
So our opinion of engineers has gone lower now. We can't even take apart desks. Nah, that's fine. I will just talk to you then. Okay, so let's see. All right, so today I will try and finish my volume, and the next week we'll start talking about turbulence. And if you remember, we had the advection equation, where we had d phi by dx dt plus dot phi u equals 0, right? Then we said by volume discretization makes this by I n plus 1, right? And the advection, this spatial term goes as flux east minus flux west over delta x equal 0. Okay, and we said flux east is equal to phi east u east, and similarly for the west. Okay, now we have our I plus 1, I minus 1, and we have the faces. and west. Again, as we've been talking about, we store the velocity at the faces and the cell averages at the centers. Okay, so in memory we only have the phi bar values. How can we get phi e? So if I gave you phi bar, looks like, so it has some value, this value, this value, this value, and this value. So this would be the phi axis, right? Phi bar as a function of x. Okay, so if I tell you at these node points, the stored value of phi bar is this much, or that much, or that much. What would you do to give me an estimate for phi east?
Interpolate.
All right, so you want me to do linear interpolation. This, right? And this would be the value that we want, phi east. Okay. So we can say phi east is half, assuming that everything is uniform, and this is delta x by 2, delta x by 2, right? So it's half of the phi bar I and phi bar I plus 1. All right. Similarly, phi west, we can write is half of I minus 1 plus. Okay, so what happens when we launch this in here? Let's see. So we have. I'm just going to take phi east, phi west, and plug this into the f east, f west. Okay. And we'll assume that u is constant for the time. Let's assume u west is equal to u west is equal to u east is equal to some constant value. Right? So which means the phi volume discretization becomes F. And we take the u over delta x out, and inside what we have is this. Phi east goes to f east, so we get phi bar I plus phi bar I plus 1 minus phi west goes to f west. Okay, so we get of course there's a 2 divided by 2. And this is phi bar I minus 1 f plus phi bar I over 2. Okay, and when we simplify this term will cancel this term. All right, and this is a 4. So what do we get? We get phi bar n plus 1 minus phi bar n 13 plus u times all right, again, does this remind you of something? What is this term?
First order central difference?
Second order center difference. Yeah, so it's estimating d phi by dx with, node right, node left, divided by 2 delta x. So this is the CD2 basically. CD2 is second order center difference. pure advection we're talking about. What do you remember happens when we do pure advection with CD2? Do you remember with advection equations, you always have to use biased stencil upwinding?
Yeah.
And the reason for that was?
It's unstable?
Yeah, so the same problem will happen here. If we take the estimate of the self face values to be the average from left to right, we actually recover CD2 in terms of finite differences. So this would be unstable if we are talking about pure regression. This discretization is unstable. And again, you can do this von Neumann analysis that we talked about. Okay, and again, this is equivalent to saying that del phi by del x is phi I plus 1 minus phi I minus 1 over 2 delta x. Okay, in the finite difference schemes. And we looked at exactly that. We used this term in a finite difference scheme, and we said von Neumann analysis. We proved that von Neumann analysis is unconditionally unstable, so not useful, right? Not useful. All right. So what would you do?
Do something besides a linear interpolation to find.
Sure. So you're saying that you want to use some other form of, some other way of expressing E, right? That's what you're saying. So we can actually do the same thing we did for finite difference. We can use upwinding, right? And we will come to that. But people tried several things, and there are schemes after scheme named for these people. You know, they were doing numerics early on, and they tried simple things, but their names got attached to these. So I will just mention one of them. It's to solve this issue of instability. They came up with something called the Lax-Friedrichs method. Okay. And what it says is, instead of doing phi bar n plus 1 is equal to phi bar n I minus u delta d over 2 delta x. So this is, I've basically rewritten this equation. Right? I took this to the other side, multiplied with delta t. So instead of doing that, we do a slightly different approximation. Okay, we say, all right, this is not phi I anymore. We replace it with the average of phi I minus 1 bar plus phi I plus 1 bar. Okay, and that guy comes as is. Okay, so all that has happened is this has been replaced with this. Okay, that's what Lax-Friedrichs method entails. Okay, so it turns out that this discretization is now stable. And why does that happen? That happens because, so this discretization is stable. And the reason for that is so to make the reason become clear, let's add and subtract phi bar I and from the RHS, from the right hand side. Okay, so let's see. This we can write as phi bar in plus 1 equal. Okay, I will add this, what I said, alright. Okay, I'll copy this term, the negative thing, let's see, minus u delta t over 2 delta x phi bar I plus 1. Alright, and then the first term I have not written down yet, so let me write that down. I have this I minus 1 and I plus 1 and then I said, alright, since I'm adding something here, I will subtract something. I will subtract the same thing, right? And this is true because there's a half over here. Okay, so this equation is exactly equal to this equation. I've just added one term and subtracted the same term. Okay, so do you see this now looks, what does this look like now? So we were talking about pure advection, right? Yeah, go ahead. Wait, no. So does this remind you of something? So the first line looks like a discretization for it looks like a discretization for the pure advection equation. So we have a, if you take this that side, divide by delta t, d phi by dt, and this is a u, there's a d phi by dx. Okay? And this is what was unstable. This is the center difference, second order. But now we've added an extra term, right? What does this extra term look like to you? If I rewrite this as, let's see, if I say it's delta x squared over 2 phi I plus 1 n minus 2 phi I n plus phi I minus 1 n over delta x squared. So I didn't do anything, I just multiplied delta x squared divided by it, right? What does this look like now?
Second order, second derivative?
Yeah, this looks like a d2 phi over dx squared. So this is the delta x squared over 2 times del 2 phi over del x squared. Right? And this is now called numerical diffusion. Alright. So what has Lax-Friedrichs done? It has taken the original advection diffusion equation and added an extra term that acts as a diffusion term. Okay. And this makes the scheme stable. Right? Of course, you know it's stable, but does that mean it's accurate? No. Things that should not have diffused will start diffusing now. It will behave as if there's physical diffusion. And the same thing happened when we were using first order advection with finite differences. You remember there was a nice Gaussian bell which started decreasing in value, right? So the numerical diffusion term makes the scheme stable but accuracy suffers. Significantly. Okay, let me just point out that this looks like the original CD2 discretization. Plus some additional terms. Okay, and another drawback of doing this is whenever there's if you're advecting a sharp gradient like this, what you will see is you will develop spurious numerical oscillations right at the jump. Okay. Spurious. May develop. They will develop at sharp gradients. So people actually started looking to mitigate this. Of course, if you do compressible flows, these shocks are very important. The properties of the fluid, such as temperature, density, changes almost instantaneously, going from one side to the other. Here, density might be 10,000 kilograms per meter cube, whereas on this side it's only 1,000 kilograms per meter. So that's what shocks represent. And if you start thinking about it, if this is your density profile, and let's say this is vacuum, so let's say this is rho equals 0 and rho equals 1, for instance. Rho goes to 1.1 over here. Is that a problem? That's a problem, but it's not out of the realm of possibility. The density can increase, right? Physically feasible. What happens here?
And it's non-zero.
Yeah, let's say it's minus 0.1. Physically, what does that mean? It means we have antimatter. So that's a big issue. That's why trying to suppress these sort of oscillations is one of the biggest. It was a big area of research about 20, 30 years ago. Okay. All right. So that's accomplished using something called flux limiters. I will talk about those in a minute. So, all right. Why did we talk about Lax-Friedrichs? Because our original center difference at pure advection was unstable, so they came up with a way of making this stable. And you mentioned we can do upwinding, right? That's another approach. So let's see, what would we do with upwinding? So another alternative for stable advection is to use upwinding. Okay. And it's very, very straightforward. So instead of using the center difference approximation, what we do is use phi bar I n plus 1 equal I n. What should we do? So what would you do? We know what upweighting involves. What do you write here?
If U is positive,
Alright. So if U is positive,
to U delta T over 2 delta X. Actually, just over delta X. Phi I plus 1 minus phi I.
U is positive, right?
Oh, I minus 1. I minus 1.
Yeah. Right, makes sense. Because you have the let's say I minus 1 plus 1, I minus 1. We're looking at yeah, we're looking at this. So if we say U is positive, you use these two, and that goes there, right? And if U is negative, it's what?
U delta T phi I plus 1 minus phi I over delta X.
Yeah. So that's the simplest upwinding you can do. This is first order upwind. Okay. Is this? Are we happy with this? Should we use this? If you remember, first order schemes have a lot of diffusion. So it was one of the projects. The profile which should convect unchanged actually changes a lot in that. So the first order method, fine, it will be stable, but again, the accuracy will be terrible. So we will look at higher order methods, right? Doing this interpolation with higher order methods. But first, so this actually has another interpretation. All right, so let's write it out. So another interpretation of upwinding okay, if I give you, let's say, a Gaussian profile, an initial profile, right? And this looks like phi naught of x. And I ask you for pure advection, how can I write phi of x comma t? And I give you constant velocity of advection is this. Analytically, what is the formula? Okay, let's forget about analytically. Well, here, if we just draw the graph, what will happen? After 1 second, let's say U is going this way with 1 meters per second, right? What would happen? Not diffusion, no weird stuff, just pure convection.
Be the same curve, but a meter to the right.
Yeah, this would be the same thing, but just the center would go from 0 meters to 1 meter after 1 second, right? And after 2 seconds, it will be at 2 meters, etc. So analytically, we can write phi x comma t as, do you remember? Or can you, I mean, based on what you just told me, yeah, go on.
I naught x plus 1.
Y plus 1.
Minus 1.
Minus 1. Why 1?
Minus u.
X has meters, u has meters per second.
Oh. So be u divided by delta t, or divided by t.
U times t.
Oh.
Right. So minus u. Yeah, so, you know, if I plug in t equal 1, u equal 1, this phi naught x minus 1 will be exactly the dashed line, right? So we know that's how pure advection works. So since we've been talking about cells, we can think of it in the same way. So let's draw some finite volume cells. Okay, let's see. So we have, let's just draw 2 of them. This is 5 bar I minus 1. All right, and this is delta x. Okay, so if we say that u is positive and constant for this case, what is going to physically happen? What's going to happen to the stuff from cell to the left and stuff from cell to the right?
They're both going to advect.
Yeah, they're both going to get shifted towards the right, right? So let's see. How much stuff should I take from left cell and advect it to the right cell? So if my time step I say is delta t, how much stuff would move from left to right?
U delta t.
Yeah, it's, you know, however much stuff is contained in this region, right? U delta t. So all the stuff that's contained in this shaded region will move to the right, and the same for this cell. So this stuff will move out of the cell. Okay. And again, phi I and phi I minus 1 are not the same. So stuff that moves in is what? Not exactly u delta t, but
Negative.
once more.
Is there any negative sign minus u delta t?
No, u delta t is correct, but u delta t is just distance, right? I want mass that moves in or phi that moves in. What does phi bar represent?
Average scalar in the cell.
Yeah, all right. So phi bar is the average value.
So it'd be 5 bar u delta t over delta x.
Phi bar I minus 1 u delta t. Let me see, will there be a delta x?
I guess not.
No, not. Because when you want the full cell content, you take phi bar multiplied by delta x. When you want only this partial cell, yeah, so, okay, you're right, yeah. It should be, no. No, this is correct, yeah, this is correct. All right, and stuff moving out of cell I, is what?
Excuse me, I don't understand the meaning of phi delta x. U delta t is delta x, right?
No, delta x is the cell size. See, if you say u delta t is equal to delta x, this will always be 1 over 2, right?
Yes.
Right, 1 over 2. So, does this make sense? Delta x is the grid size you establish. U and delta t can change. Okay. So, how much is this?
So phi I u delta t.
Phi I u delta t. All right, perfect. So stuff remaining in cell I. So all right, fine. So and stuff in cell I is equal to what?
Phi I delta x plus stuff moving in minus stuff moving out.
Perfect. The stuff moving in is this, and minus stuff moving out is this. Make sense? So initial amount of phi contained in the cell plus phi coming in minus phi going out. Right? And when we simplify all of this, and again, net stuff in cell I at next step, so I can just write this as phi I m plus 1 delta x. Right? Right? So that's what happens at the next action. Okay? Is equal to basically, yeah, the same, the right hand side. Which means, what have we recovered? We have recovered phi I bar plus u delta t times phi I minus 1, minus, let's put a minus there, times phi I bar over delta x, which is what?
Pure advection.
Yeah, this is pure advection with upwinding, right? This is the same exact thing we wrote over here, right? Okay, so we have recovered upwinding. Recovered the upwinded formula. Okay, so that's another interpretation of upwinding. Basically, looking at information that's coming in, looking at the information that's going on. Okay, so let's see. All right, and then we were talking about, okay, that doesn't seem very smart to use just two cells, or upwind just using what's to my left or what's to my right. Let's do something more involved. So let's do higher order interpolating series. Okay, and this is again in the context of upwinding. So let's see, we have cell 1, 2, 3, 4, right? We have I minus 1, I plus 1, I plus 2, and we have I minus 2. Okay. And this is our main cell of interest. All right, and again, we know all the values stored over here. So let's say this is this much, this is this much, and this is this much. And okay, and over here we have this. that's something. Okay, perfect. So now we have west and east. Can you give me a good estimate for phi west? How should I write phi west? Phi west. So that's the first thing we tried. We did a linear interpolation between these two. What else can you do? Okay, let's make this a little easier. Let's say U west is this way. And you know, with pure advection, you should always try to use the information that's relevant. So what information is relevant for this cell phase?
I minus 2 and I minus 1.
Yeah, so we should potentially try to use I minus 2, I minus 1 instead of things on the right, right? So let's see, we have 3 points of interest. Our cell point, 1 left, 2 left. What can we fit?
Polynomial.
All right, what polynomial?
Third order.
Parabola, yeah. Right? So we can fit this polynomial and this is our value that we want. Okay? So 5w can be computed using a parabola fit to the 3 upwinded points. See, if I said use 4 points, then it would be a centered stencil. 2 to the left of the face, 2 to the right of the face. But we know centered stencils always cause trouble when doing pure advection. So we are going with high order upwinded interpolation. Okay, and this exact scheme is called quick. It's a very popular scheme. QURK and it's quadratic, upwind, convective. What is the K for? Kinematics. Okay. Wait, not upwind, upstream. Come on. Upstream interpolation for convective kinematics. And that's one very important thing you have to do when you do numerical work. You know, you have to come up with cool names so people will use it, right? So you have Q, U, I, E. Okay, so does that make sense? And if you wanted to go even higher, you would use 2 to the right, 3 to the left. And then we go into the purview of Wemo schemes. So they do exactly this and some fancy combination of stencils. Okay, and let me see. So fine, well, you can actually fit the parabola since you have, you know, the 3 points you need. So phi w would just be some a plus bx plus cx squared, right? For fitting. Okay, and when you do all the mathematics, the formula actually comes out to be phi west is 3 over 8, yeah, 3 over 8 phi self plus 6 over 8 phi left minus 1 over 8 phi left. What if I told you UW was negative? What would you do?
Flip it.
Be using I plus 1 and I plus 2.
Plus 2, I plus 2. Okay, so let me write this, let me draw the cell picture again. Right. 1, 2, 3, 4, 5, right? We have I minus 2, I minus 1, I plus 1, I plus 2. And we are interested in cell velocity. And I give you, again, these are the 5-bar values. Okay. And now U goes this way. And you said I should use I plus 1, I plus 2? Yeah. Anybody have another answer?
Just I and I plus 1.
Only I and I plus 1?
And
Can I change mine?
Of course.
I minus 1.
I minus 1 is 3.
Yeah, these three, because see, it's still upwinded with respect to our cell phase. We're not talking about upwinding with respect to the node, right? So if we want value here, the two important values where information is coming from are to the right, and we will use 1 to the left. Okay. So we would use this parabola instead. And this would be our required value. Okay, so see, the x's are at the same locations as before, but our parabola that we use has changed from the left biased parabola to the right biased parabola. And that's it, that's all the quick scheme does. You just keep checking what your current u is, the sign, and then you use the correct stencil. Done. Okay? And I think most computations, a lot of computations are done with quick because it's relatively simple and inexpensive. Any questions? Okay, so how does it compare in terms of accuracy? Let's go and look at comparison of quick and upwind. Okay. So analytically, it should be the gray line, the flat, and then almost vertical, and then flat again. If we implement upstream as basically first order of upwind, where you just go left or you just go right, you get a huge smoothing of the function, which is not desirable. Right? This is the numerical diffusion that comes into it. And if we use quick, that's the green line, our smoothing is not as bad, but now we have oscillations. And do you know why there's oscillations? Do you know of a guy called Godunov? No? Okay. So Godunov was a very famous mathematician. Probably is, a Russian mathematician who wrote a very short thesis for his PhD. I think it was 10 or 15 pages, in which he proved that no high order scheme can avoid this problem. If you have any scheme that's higher than first order accurate, you will get such oscillations. Okay? So that's proof, that's a theorem. So, and that's a huge issue, right? Because then, whenever we talk about shocks, forget about high order schemes. This will kill the physical meaning of the simulation. Okay? So, how would you fix this? What would you do? What did we say? The only way to suppress this issue is what did Godunov say? The only way to suppress this issue is
To add points to
it doesn't matter actually. Let me go to the next one. All right. So there you have a 20 points versus 40 points versus 80 points. The curve gets sharper, but the oscillation gets worse. Do you notice that? Red to green to black is actually getting worse. At some point it will level out. This is called a Runge's phenomenon. Okay, so adding more points does not help. Okay, so let's see. Let me write down Godunov's theorem, and then maybe you can tell me. So, Godunov's theorem is monotonic. Yeah, fine, monotonic schemes, which means non-oscillatory. Can be at best first order accurate. Which means that high order schemes will generate spurious extrema. Right? And again, is that becoming that, which is physically it can be terrible if this is density, for instance, or temperature. Temperature going negative. Negative in kelvins, meaningless. Okay, so, all right, now that you know what Godunov said and you know you need to fix this problem, what would you do? Okay, so think about it. What is the only way to avoid this problem?
Staying first order.
Yeah, the only way to avoid this problem is to stay first order accurate. But away from this, very localized region, you don't want to be first order. It's terrible for accuracy. So we cannot avoid staying first order here. So let's use some scheme that's first order here. And
Use higher order schemes.
yeah, exactly. As we move away from this sharp discontinuity, let's switch to higher order schemes. Okay? And that's exactly the fix they came up with. So they use high order schemes away from the discontinuity, and as you come closer, you switch to the first order scheme. Okay. And that's what's used today for most supersonic or compressible flow simulations. All right, so the solution was to use something called flux limiters, or I almost wrote flux capacitor. Or slope limiters. Do you know what flux capacitors are?
Back to the future, right?
Yeah. You have not watched Back to the Future. You need to watch all five of them. Five? Yeah, five. So go ahead and go. It sounds very technical, but it doesn't really exist in reality. Okay, the flux capacitor. All right. So flux limiters, what do they do? What they do is, let me write our advection equation again. So we have 5r I n plus 1 minus 5r n plus n I delta t plus no, not u, f is minus s over delta. Sorry. Okay, and this is again phi east u east. All right, and this can be approximated using quick, for instance. All right, what the flux limiter does is, this is FE. Flux limiter modifies FE such that phi E is computed using high order schemes away from discontinuities. And the first order scheme close to the discontinuity. Okay, so it acts as a switch basically. And if we talk about, let's say you're interested in affecting a profile that looks like this, okay? So in this region, you would want to use, because at gradients, you'd want to use a first order flux. And in the smooth, nice region, you would want to use high order flux. Okay, and for doing this sort of switch, you have to have some way of identifying what region are you in. Are you in a smooth region, or are you in a this continuity region? How would you do that? If I just gave you this profile and tell me which region is smooth, which region is sharp, you just look at it and tell me, right? But how would you do that mathematically, numerically? The computer cannot do that, right? So we have to tell it some way.
Taking a derivative?
Yeah, you can take a derivative, right? But it went with something similar. Derivatives here are infinite, right? Spatial derivatives at the sharp interval. So what they have to do was they have to say, okay, I will take a ratio R, and I will say it's I minus 1, or I think it's I minus 1, let me check. Yeah, so it's phi bar I and minus phi, and this is in I minus 1, and divided by or I plus 1 and minus phi bar I n. Okay, and when we are in a smooth region, what is the value of R? When we are in a smooth region, what does that mean? Changes in phi are
Round one?
Yeah, the ratio would be roughly 1, right? So let's see, this would be roughly 1 in smooth regions. And it would be, let's say, would be very different from 1.
Maybe the absolute value.
No, not absolute. I will tell you why.
No, for Ri, the absolute value of Ri is bigger than 1, then that's definitely.
Oh, that's what you mean, yeah, so
Yes.
it's plus minus 1, yeah. Okay, it's,
No, if we define, first we define,
no, I don't want to put an absolute value here. There's a reason for that.
so we can in the right side say, okay, absolute value of Ri, if it's bigger than 1, or high bigger, very larger than 1, that's definitely.
Not just larger than 1,
If it's between 0 and 1 or 0 and -1,
that's also a problem. See, because if these two numbers are very large, the ratio might be 0. Right? If these two numbers are, that's what happens at shocks, right? So you want to be as close to 1 as possible. Any deviation from 1 means the region is getting non-smooth. Okay? So this is sort of an indicator of smoothness. Right? And how is this used? This Ri actually goes into, let's say, flux. E is defined as flux hat E, yeah, plus flux tilde E minus flux hat E times C of R. All right. So what are these? These are nothing but this guy is the first order non-oscillatory interpolation for phi E. Okay, and this guy is the high order estimate for phi E U. Let's assume U is constant. Okay. And the C acts as the switch. If C is equal to 1, what do we get?
Fe tilde.
Fe is equal to F tilde E, which means high order only. Right? And if CR is equal to 0, what do we get? A fat, which means, what does it mean?
Smooth.
Very smooth.
Sorry.
So high order estimate means smooth region, right? We are only allowed to use high order estimates if the region is smooth. Sharp regions, high order not allowed, right? Fine. So if CR is equal to 0, which means we are now
Linear, first order, linear.
yeah, we need to use a first order only, right? And this means we are close to a shock or a discontinuity. So this makes sense? All right. And this C, it depends on the ratio that we define, and people came up with many different ways of defining C. And everybody who came up with a different method got their name attached to it. Okay? So let's see. Let me write out a few of the most popular ones. So let's see. Several popular limiters. Okay, one of the most used ones is called super B limiter. Super B limiter. They should make a movie on this now. Like they have Ant-Man, they have Batman, they should have a B-Man. Or super B. Okay, so super B limiter says CR is equal to max of 0 or mean of 1, 2r, or mean of r, 2. Okay? So, again, this is very simple. At any point, we are looking at point I, and we have our neighbor left, neighbor right, we compute this ratio, and plug it in here. This gives us our C. And then we plug in the C here. F tilde can be our quick approximation, and F hat can be our first order outgoing approximation. That's it, done. That's, you've implemented a flux limited finite volume affection scheme. Make sense? Should I repeat that?
Your last statement, sorry.
When you plug everything we have talked about in here, you have implemented a flux limiter finite volume scheme. So you will be able to simulate things with shocks. There's nothing complicated, it's just very simple things. Does this make sense?
How exactly is the value of R put in there? What's
It's here. So R does not go directly into computing the flux. R goes into computing CR. And CR depends on R as this. So when you compute R, you compute the minimum of 1 or 2R, right? Compute the minimum of R, 2. And then you have 3 numbers, you take the maximum of that.
okay?
So that gives you one value. That value is the factor that goes here. Make sense?
Yeah.
So if we look at simpler limiters, let's see, what's the next one? Next one is Van Leer, all right? So this is Van Leer. Van Leer limiter is defined as R plus R over 1 plus R. Okay, so again, you compute R for your current cell. You compute this very simple function. That's your factor that goes over here. All right, there's 2 more. There's actually many more, but I will tell you 2 more.
Vermonitor.
Okay, what?
You don't have any Vermonitor.
Who?
You haven't,
Oh, mine, yeah. No, I was born too late. This was being done in the 60s and 50s. So yeah, they took all the nice ones. So this is CR max of 0, mean of 1, R. Okay, and then the last one is muscle, MUSCL. Muscle means monotonic upwind scheme for conservation laws. See, you have to come up with cool names for your schemes so people can remember and use them. There's another one called, I will not tell you detail, but awesome, wait, let me create it down. Yeah, there's this. How do you read this? Sorry, this one.
some food.
It's the awesome scheme. And then there's an awesome plus scheme, right? So, yeah. So muscle scheme is how? Muscle scheme is a TR is max of 0 of mean of 2R, R plus 1, divided by 2, 2. Okay, and there's reasons for why they pick these. There's stability regions, etc. But those are details. You can go and look at those if you like. But if you just want to implement these are 4 good candidates to implement in your shop capable finite volume scheme. Okay, does this make sense?
Does that happen only for a shock or a...
Yeah, you don't want to use a low order scheme when you don't have a shock. The only problem the high order schemes cause is near a shock, they oscillate. Okay? You always want to have high order schemes. If you remember from projects, anytime you implement low order schemes, they would diffuse out very, very quickly. So they're not very active. Is this good? All right. So the very last thing I want to tell you about finite volume schemes is actually related to what we just talked about. DVD. DVD is called total variation diminishing. Schemes. Okay. So total variation diminishing schemes are just numerical schemes that ensure that you will not generate additional variation. So you will not generate these spurious extrema. Okay. And the only condition for the condition that you need for that is, let's see, so TB is defined as, total variation is defined as summation of I, phi, I plus 1 minus phi, right? Simple, right? You're basically summing up changes from one cell to the next over your whole domain, right? And for TBD to be valid means TB at n plus 1 is less than or equal to TB. This should be guaranteed, okay, no matter what. And the limiters that I showed you here, these schemes actually you can prove that they're TDD. Okay? So that's another good property for schemes to have. Do not generate extrema that should not exist. Again, there's a whole literature on these schemes. People wrote books and books about this. I don't know if this is still active research. I don't think so. Okay. All right. So you know how to go from partial differential equations to the integral form, to the surface integrals, to the finite volume discretization, and we've looked at how to compute. The most important thing is you store average values at the cell center, but we need fluxes at the cell faces, and we've looked at how to go from one to the other by using some sort of interpolation, and we've looked at what happens, what are the problems that can come up with high order interpolations, and how to fix those using these flux limiters. Okay. So now you know most of everything you need to know, the basics of finite volume methods. All right. So the main focus of our class has been on doing finite differences, and then we talked about several methods, roughly. So we talked about spectral methods, we talked about vortex methods, and now finite volume. But the one thing we did not talk about is physics. Physically, it's always important that you take care that your simulation is able to represent the smallest length scales and time scales that are important in the physical problem, right? And that's where the concept of doing turbulence simulations comes into play. So the next two classes, I will talk about briefly about what is turbulence, what is involved, and some modeling aspects of turbulence. How do people cope with the issue of this mix? The space scales are too small. What should I do? I don't have enough computing power to resolve all of this. Okay, so we will do that Tuesday and Tuesday after. And please don't forget the project. It will take time, so start early. Any questions for now?
No class next Thursday then?
Next Tuesday we have class. Next Thursday, no class. Yes. And I sent the announcement a while back.
That's right.
No class April 11th and no class April 18th. Alright, so I'll see you next Tuesday. Wait. I forgot to show you the graph with the flux limiters. this is what the flux limiters are able to do. So no more oscillations, spurious oscillations, and you see all of them work pretty well. Some work better than the others. But in smooth regions, these will be terrible. So you should not use the limiters in smooth regions. That's why we have the switch.